Okay, let's prove this interesting looking theorem. A is empty if and only if A has 0 elements. So if I had shown you a theorem like this a few days ago, probably you would think that it's so obvious as to be difficult to prove, right? Like, how is this not just true by the definition of having 0 elements or something like that? But a few days ago, we had not defined this concept of having 0 elements. Now it's defined. And also is empty. I think we never really defined that term, or that predicate officially, but we used the idea here in the title of a theorem. So, and we used it here also, I guess. So what does it mean to be empty? It means to have no elements. So let's see if we can. The first part, and maybe the biggest challenge in this theorem, is to figure out what it is we're even trying to prove. We must prove that, and then it's an if and only if. But we need to sort of translate this into some formal language. So what does is empty mean? A is empty. That means A contains no elements. Okay, you might have thought that is empty means A equals the empty set, right? And if you thought that, you would also be correct. That's not technically the meaning, I guess. Well, there's nothing technical since we never defined is empty. But since we argued that the empty set is the unique set that is empty, to say that A has no elements is to say that it equals the empty set. So this has long been proven for us, and so saying this or saying this are the same. So let's just go ahead and accept that as what it means to say a set is empty. Okay, and then what does it mean to say it has 0 elements? It means 0 is a natural number, and so do you see where I'm getting this? I'm just reading off the definition of having n elements. Having 0 elements is this statement. 0 is a natural number, and the set is in bijection with 0, or has the same cardinality as 0. Oh yeah, we started the proof. So let's work on this one. And I mean, we don't really have to worry about this, right? 0 is a natural number because the natural numbers are inductive, an inductive set, so they contain 0. So let's just keep the interesting parts here. Oops. And let's just say, since we know 0 is a natural number. Okay, so left implies right. Assume A is the empty set, then A literally is 0, right? Because 0 is the empty set. So, how about, so what we're trying to prove then is that 0 has the same cardinality as 0. But coming back here, that's just a reflexivity statement, right? It follows by reflexivity of the wiggly equal sign. So by, what was it, theorem 115.1, yeah, I guess. How about to make this a since? Since by theorem 115.1, we have 0, wiggly equals 0, it follows that A, wiggly equals 0. Okay, so that direction was easy. Let's do the other direction. By the way, this is, I think this is actually a pretty misleading theorem. This is a pretty misleading example of a proof to go through, because when you start, usually when you're showing that a set has n elements, you're not trying to show that set literally is n. That only happens pretty much with 0. So this is kind of special, that having 0 elements makes you actually equal 0. Normally having n elements doesn't make you equal n, right? How about I give you an example of that after this proof? Okay, so let's do the other direction. So now assume A wiggly equals 0. Now I want to prove that A is empty. So how do I make use of this? Well, this is an existence statement. It's telling me that there exists a bijection from A to there. So we can get one, right? This is existential instantiation. Get a bijection. F A to 0. Now, my goal is to argue that A is the empty set. So why do we think that the existence of this bijection implies that A is the empty set? Why would we think that? Let me draw a picture and think about it. So here's maybe my picture of A. Here's my picture of the empty set. A could have stuff in it, or maybe it has no stuff in it. I'd like to prove that A has no stuff in it. Here's my picture of the empty set. There's nothing in here. So what if A did have stuff in it? So let's say here's something. I open up A and I find there's something there. How is that contradictory? This should somehow lead to a contradiction. Well, if I apply F to that, whatever item I found in there, F of the thing that's there, then that ends me up at something in the empty set, right? That ends me up in here. That's the contradiction. So I could say, okay, suppose A is non-empty for the sake of contradiction. Then it has an element, and then F of that element is in 0. But 0 is the empty set. So that's a contradiction. I wonder if there's another more direct way, like thinking about the range of F. Yeah, maybe. How about actually this idea? If F is a function, which our F is, then F maps one thing to another if and only if it's a subset of the Cartesian product, and blah, blah, blah. So by theorem 55, since F is a function mapping A to there, F is a subset of this, right? Which, by the way, is this. Since 0 is the empty set, it's this Cartesian product. But if you Cartesian product something with the empty set, you just get the empty set. Do we have that somewhere? Yeah, theorem 43, part 2. A Cartesian product is empty if and only if either one of the two factors is empty. So this is by theorem 43, part 2. And so F is a subset of the empty set, so F equals the empty set, right? By the minimality of the empty set theorem. Well, actually, my goal was to show that A is the empty set, but now I've shown that F is the empty function. Well, A is the domain of F, so it's the domain of the empty set, which is the empty set. How about that? So we have shown that a set is empty if and only if it has 0 elements. And again, this is kind of misleading of a situation, I think, because you don't usually have a set having n elements ending up being literally n. So here is an example. Oops. let's let A be the set 0, 2. How about 0, 3? Then, do you think A has 2 elements? Probably, right? Probably this A has 2 elements. How would you prove A has 2 elements? You could say let F be this set of pairs. 0, how about 0, 0, and 1, 3. Do you see why I'm doing this? It's because I'm trying to write a bijection between A, which consists of 0 and 3, and 2, which consists of 0 and 1. And I'm setting up my bijection to do this. Now, if you can prove this is injective and surjective, then you will have proven that you have a bijection from A onto 2. That will prove that A has the same number of elements as 2. Or in other words, A has 2 elements. Okay, so here A has 2 elements. But would you say A is 2? Absolutely not, right? Absolutely not. For one thing, I mean, they share an element, which is 0. A and 2 definitely both have 0 as an element. But 3 is not an element of 2. But 3 is an element of A in this situation. Do you see how I know 3 is not an element of 2? It's because to say 3 is an element of 2 is to say 3 is less than 2. See the big advantage of our framework here? To say 3 is an element of 2 is to say 3 is less than 2. These are the same. 3 is less than 2, 3 is an element of 2. And we know 3 is less than 2 cannot be true because 2 is less than 3 is true. Things are always less than their own next. And we have the trichotomy law. You cannot have both of these being true. So 3 is not in 2, but 3 is in our set A here. And so A cannot be equal to 2. Let's prove a less misleading, I think, version of what we just proved. The empty if and only has 0 elements. How about a set is a singleton if and only if it has 1 element. And here you see I'm writing the natural number 1, right? Just like here I wrote the natural number 0 because I'm writing has n elements with 0 in for n, or with 1 in for n. So if you wrote the word 1 here, then you would sort of be at the wrong level of language. You would be using the English, sort of Englishy language that the document or that your formal language is explained in, so the language that this document, for example, is written in, rather than using the formal language itself. So let's look at what is it that we're proving here. Set is a singleton. What does it mean to be a singleton? What does it mean to have 1 element? To be a singleton is this one we actually defined. Right down here, definition 24, being a singleton. So to be a singleton is to be something that you can write, that is possible to write as a singleton. So it's to be equal to singleton of something, something. So a set, how about instead of saying a set, how about we say A? A is a singleton if and only if it has 1 element. So to say A is a singleton, we must prove the following. To say A is a singleton is to say there exists X such that A is the singleton of X. And to say A has 1 element is to say 1 is a natural number, which we know since it's the next of 0, which is a natural number. And, more interestingly, is to say that A has the same number of elements as 1. Now, I'm going to remove this part since I'm going to say that that's very easy to prove that part of it. And I'll just point out this is sufficient since 1 is a natural number. Maybe if I were being less lazy, I would spell things out here, but that's fine. Let's focus on the important aspects, or the interesting aspects. So assume A is a singleton. So in other words, we're assuming this. Then we can get x such that A is the singleton of x. Now, can I prove that there's a bijection between A and 1? So here's my picture. Here's A. It looks like A just has x in it and nothing else. And here's my picture of 1. 1 is a set that consists of 0 and nothing else. So can you think of a way of connecting some green arrows from here to there so that you have a bijection? Should be pretty easy, right? Just this. Remember, each one of these arrows represents one ordered pair that's in F. So it looks like we're saying let F equal this pair. Or rather, let F equal the singleton of this pair. So F is this set of pairs with just one pair in it. And then, I don't want to go through this, but let's now say insert proof that F maps singleton X to singleton 0 bijectively. So let's suppose you finish that, and then that would prove that A has the same number of elements as 1. And for the other direction, sorry that I'm rushing, I'm trying to fit everything into the time block that I've got, and I'm trying to get to the part that I think might be a little bit misleading from the previous proof. So suppose A has one element, then we can get actually I think we already reached that misleading looking part. So in the 0 version of this result, in this direction when we assumed A was the empty set, we managed to prove A actually is 0, right? That's how we showed A has 0 elements. We showed it is 0. But here it's not like that, right? It's not that A is 1. A could be not 1, right? 1 is singleton 0, but A could be singleton something else. A could be singleton 7, right? Or it could be singleton 7 even, which would be different. Or it could be singleton the sine function or something. A could be any kind of singleton. And so the goal here was to establish this bijection. So I think you've already seen the important part here. And yeah, so then what I'm leaving out is proving that this is a bijection and that it maps this to that. Okay. So here, for this, when you're trying to show that A is a singleton from here, you would say get. So this is an existence statement, right? It's saying there exists a bijection, A to 1. So it enables this existential instantiation. We can get a bijection. F mapping A to 1. So now your goal would be to prove that A is a singleton. So your goal would be prove that A is singleton X for some X. And how might you do that? So can you come up with an X such that A is singleton X? So here I would say, so let me draw a picture and see how I'm thinking about this. I've got this bijection, it's been granted to me, F, and it goes from A to 1. And I don't know what the contents of A look like here, unlike up there, right? Up there I knew exactly what A looked like because I was assuming that it's a singleton. But down here I don't immediately know what the contents of A look like, but I know I've got this bijection, and I know the contents of 1. 1 is the singleton of 0. So given the bijectiveness of F, can you come up with an element here, and then can you prove that it's the only element? If you can do that, then you would prove that A is a singleton. So how would you come up with an element here? Maybe I'll end the lecture there, and I'll just say, see if you can figure this out. I'll give you a version of this kind of problem, maybe the number 2 version rather than 1, for your homework. But here, where I'm leaving it open, somehow you have to use the injectivity or maybe surjectivity of F to show that A has an element and that it has a unique element.